Thank you for the presentation. I'm going to present some of my work carried out within the GreenCarbon framework, of which I'm one of the 14 researchers. And today, in particular, my field of research lays in the work package related to refining of biochars and advanced applications. So let's start with a small introduction about the biochar, which is a carbon amorphous aromatic material, which, depending on its feature, could be employed as soil amendment, in catalysis, or as pollutant removal. But the most important feature which a biochar must have is a high surface area in order to be employed in the above-mentioned applications. And as you can see from the table, a pristine biochar produced at 500 degrees C and 0.1 megapascal from slow pyrolysis of wheat straw biochar, or wheat straw, only has 1.68 square meter per gram, which almost zero. So in order to improve its textural properties, the biochar needs to be activated, which means the surface area needs to be expanded. There are several methods to activate a biochar, and the one I choose for my study is the physical activation with CO2, which is basically a partial gasification at high temperature of the surface carbon of the material, which produce CO, leaving defects on the surface. As you can see, these are the results obtained with an activation at 800 degrees C and 0.1 megapascal. You can see that we were able to reach, after 40 minutes of activation, a pretty high surface area, which was 850 degrees C, 850 square meters per gram. So, along with biochar, during the slow pyrolysis of a biomass, is also a liquid is also produced. This liquid is called pyrolysis oil, and it's a very complex mixture of more than 100 compounds, which you can see some of them in this table. And the main drawbacks with this bio-oil is that it has a very high water content, depending on the process, which make it not usable as fuel, not employable as for fuel applications. And its heterogeneous composition depends strictly on the process and on the feedstock. And the most important one is that it can condense in the reactor or in the pipe system or in the heat exchangers, causing breakdown of the system. So the solution could be represented by the steam reforming of the pyrolysis oil, in which no external water is needed because of the high water content. And we can produce more valuable permanent gases, rich in hydrogen and carbon monoxide, which can be then further supplied to other processes. So the main objectives of my work that I'm going to present are two. The first one is the study of the influence of activating condition on the textural properties of the resulting activated chars, studying the temperature, but in particular the pressure, which was never reported so far. And then we choose one of the best activated carbons to be employed as catalytic support for the upgrading of the pyrolytic oil. So here we go with the first results. In order to perform the first part, so the study of the textural properties, we carried out several activations at different temperatures, from 700 to 850 degrees C, and at several pressure from 0.1 and 1 megapascals. Following an experimental design with 3 replicates of the central points. And the response variables analyzed were all the textural properties, so the surface area and the pore size distribution in terms of volume of pores. So these are the results obtained, and as you can see here, the best one in our opinion was the one activated at lowest temperature, 700 degrees C, but at highest pressure, which was 1 megapascal. And as you can see, the surface area was pretty high with an heterogeneous pore size distribution. Even though it was not included in the experimental design, we also activated biochar at 650 degrees C at 1 bar, and nevertheless, the temperature was very low for this kind of application. We could able to reach a very relatively high surface area of 447 square meters per gram. So here we have the normalized plot of the standardized effects, and the temperature named Ha in this case. You can see that has a negative effect on the on the surface area and on the volume of ultramicropores. Meanwhile, it has a positive effect on the volume of micropores and was not influenced at all for the total pore volume and for the volume of mesopores. On the other hand, we can see that the pressure instead has a positive effect for all the textural properties. These results were published in Fuel, and this work was carried out in collaboration with the Professor Vanessa Fierro. And the results showed that we can tune the properties of the biochar working with different pressure and temperature in order to obtain a pore size distribution that it's useful for our applications. As I previously said, we used the biochar activated at 700 degrees C and 1 megapascal, and we used it as support for different catalysts, monometallic and bimetallic catalysts using iron, nickel, cobalt, cerium, and potassium. These catalysts were employed as fixed bed for the similar forming of in the first stage of acetic acid, which we choose as model compound in order to perform a screening of the best catalyst, and then we try to reform a real pyrolysis oil. So here we have the results obtained for the first stage, so the reforming of acetic acid, and as you can see, the results in terms of acetic acid conversion. The best results were obtained as expected with the nickel-based catalysts. In particular, with a loading of 7%, we were able to obtain a pretty high conversion, close to the 100%. But if we also look to the pressure drops along the reactor, which we related to the coke depositions and to the hydrogen yield, we choose as the best catalyst the one with 10% of nickel, which hinder the coke deposition, and which was a good trade-off between all the variables taken into account. So we try to improve the performance of this catalyst. We try to add a second metallic phase, in particular potassium, iron, cerium, and cobalt. And the potassium was a disaster, was unstable, so the results were not shown in this presentation. And as you can see from the plots, there was an improvement of the performances, but the best catalyst was the cobalt-nickel one. With a 7% of cobalt and 10% of nickel, we were able to obtain, even at 465 degrees C, a pretty high conversion and hydrogen yield close to the equilibrium one, with no presence of acetone. So we also tried to perform a stability stress test. What we did is to change the temperature during the reaction. And as you can see in the first part of the plots, the temperature was stable to 600 degrees C, and then we cooled down the reactor to 400 degrees C, and we heat it up again. As you can see, the conversion reached after the heating step reached exactly the same value, which is good. But it's noticeable to see the peak generated for the hydrogen yield and the acetone yield, which were not linked to the improvement of the conversion. So we supposed that these peaks were related to previously adsorbed acetone and hydrogen, which were desorbed during the heating step. So this is the results obtained for the reforming of a real pyrolysis oil. As you can see, also in this case, the experiment was not successful because we could only reach a 35% of conversion, and the activity was completely lost after 65 minutes. We related this loss in conversion, loss in activity, to the presence of sugar-type compounds in the bio-oil, which go charring rather than reforming, poisoning the catalyst. So what we did is to distillate the bio-oil to get rid of these compounds. So we distillate the bio-oil at 200 degrees C and atmospheric pressure. And after an optimization of the operating conditions, so a higher temperature and a lower liquid outer space velocity, we obtained a pretty good results, I mean, because you can see here the two-step stability test for 850 minutes. After a first loss in activity, that in which the conversion goes from 85% to 65%, we cooled down the reactor and we heat it up again. And we regenerated a bit the catalyst, as you can see, because there is a small improvement of the conversion, which was gradually lost again. However, the final conversion reached a plateau value of 65% even after 850 minutes. So in our opinion, it was a very good result. And the spent catalyst was then characterized by time analysis and the presence of we also found carbon nanotubes and sintering effects. But however, these two phenomena did not cause a loss in activity of the catalyst. So to conclude, we studied the influence of pressure and temperature, in particular the pressures in activating conditions, in activating procedures, resulting to be very helpful, because even at low temperature, we can, with higher pressure, we were able to obtain high surface area and good textural properties. And the production of biochar-based catalyst was successful because we were able to reform acetic acid with a conversion value close to the 100%, and also the distilled pyrolysis oil was also carried out, the reforming. In the future, I would like to perform longer stability tests because 850 minutes are not enough, in my opinion. And I would like to optimize the formulation of the catalyst in order to be employed in the raw pyrolysis oil reforming, which is one that in which I'm really interested. Furthermore, I'm now performing CO2 methanation experiment with a biochar-based catalyst, and with Gianluca, we are trying to use the biochar as adsorbent for biogas purification, sorry. So thank you for your attention. If you have further questions, you can send me an email or here in the presentation. Thank you.
Okay, Christian. Thanks for your presentation. We have time just for one question because we are a bit delayed due to the technical problems issues.
Okay, so Przemysław, thanks for the presentation. Very interesting. I would like to ask you if you took full range of foresight.
I think this question, okay, it's for you. It's for you, okay.
I suppose yes. Yes, we use the nitrogen and the CO2 isotherms, both of them, to analyze the whole foresight distribution. I don't know if it answered your question.
Okay. So no more questions. Thanks again, Christian, for your talk.